Hello and welcome to our conversation on electron configurations. Today we'll talk about the structure of electron cloud. We'll talk about how to write electron configurations, 3 models for showing where electrons are in the atom, and then we'll end with a discussion on how to use a periodic table to do electron configurations. So this should all be a review with some new stuff thrown in first year chemistry. All right. So the electron cloud is organized into energy levels. The first energy level is the lowest energy level. It's also closest to the nucleus. It contains an S sublevel, and so the S sublevel has the shape, it has a spherical shape. Now, one thing to note here is that there are these weird regions. So here's the 1s, and you can see how the electrons are most likely here close to the middle. There's the most probability, and they're less probable but still can exist out farther away. Here in the 2s, even though it's bigger, so you can see the outside radius here is bigger than the 1s, it still has density of electrons close to the nucleus. And the same with 3s, it has a lot of density out here, so electrons spend a good deal of time far away, but some time in close to the nucleus. So those are important things to note, and we'll talk more about what that means later. Now, the S sublevel has only one orbital, and that's true of the first 1s, 2s, or 3s. No matter what energy level it's in, it only has one orbital. Each orbital can hold 2 electrons, so the S can hold a total of 2 electrons. All right. Second energy level in the electron cloud contains an S and a P. So the 2s energy level or sublevel is just bigger than the 1s and has that inside structure to it as well. The P sublevel, instead of having one orbital like the S, it has 3 orbitals, and each one is a peanut or dumbbell shape. Here's what they look like, and you can see here's that peanut dumbbell shape, and they stick into different orientations into the air. So the nucleus is here in the middle, and this one should be overlapping here and coming off along this x-axis back here. And it goes back behind that one here, and then this one would overlap here and be sticking up in the air this way, down in the air this way, and you'd get this overlapping thing. I've got a graphic here of one using balloons, and you can see that one of the P orbitals is right through here, another P orbital is vertical, and the other one is 90 degrees to that. So that's what it would look like in real space. Like that, sort of. All right. So that's a P sublevel. It has 3 orbitals. Just like any other one orbital can hold 2 electrons. So there's a total of 6 electrons in a P sublevel. 2 electrons along here, 2 along here, 2 along here. And those electrons just bounce back and forth and share that region, share that region, share that region. Total of 6 electrons. I'll write that right here. So 6 electrons from the P plus 2 electrons from the P, from the S, for a total of 8 electrons in the second energy level. All right, third energy level has an S, a P, and a D sublevel. So you'll notice each energy level adds another sublevel to it. Again, the S is just a bigger S than the 2S, and the P's, you can think of them as also just being a bigger P of the 2 P's. So everything's just getting a little farther away. And the D sublevel actually has 5 orbitals. So each of these, so there's 1 orbital, 2, 3, 4, and 5. And all of these are overlapping over the same. So again, the nucleus is down here in the middle where the X, Y, and Z axis come together. The nucleus is down here in the middle of this. It's here in the middle. And we have to overlap them all together. It's really hard to see. This shape, don't worry about. This one's no big deal. Don't worry about it. So no big deal here. Whoops. All right. But you do need to know that each orbital, like all the other sublevels, each orbital can hold 2 electrons for a total of 10 electrons in the D. So in the third energy level, we have 2 electrons in the S, plus 6 electrons in the P, plus 10 electrons in the D, and that gives us a total of 18 electrons in the third energy level. And once it says 18, it's totally chock full. All right, let's do another one. Fourth energy level has an S, a P, a D, and an F. So it adds a new shaped sublevel, and that's the F. The F doesn't have 5 orbitals, it has 7 orbitals. And they look like this. Again, this is a crazy wild shapes. They're all superimposed on each other. And what you need to know is that each of these orbitals can hold 2 electrons for a total of 14 electrons. So the fourth energy level has 2 electrons from the S plus 6 electrons from the P plus 10 electrons from the D plus 14 electrons from the F, and that equals a total of 2 plus 6 is 8, 18, 32 electrons. Awesome. So that's the structure of the electron cloud, is broken into pieces. Now as we look at how to describe where electrons are in an atom, there are 3 major ways of doing it. Let's do that quickly for the oxygen atom. The first way is the electron configuration. And the electron configuration for oxygen has 8 protons, and a neutral oxygen will also have 8 electrons. So we've got to place 8 electrons. I know my first energy level has an S sublevel, and 2 electrons can fit into that. So that's 2 of my 8, so 6 left. My next energy level is 2S, and it's going to put 2 electrons there. And then 2P, and I've used up 4. I have 4 electrons left. I put a 4 here. Now the P can hold 6, but we run out of electrons at 4. So for oxygen, 1s2, 2s2, 2p4 is electron configuration. Now the other way of doing this is with an orbital diagram. And we can do this as, so what it emphasizes here, we have 1s, and we draw a box for every orbital in that sublevel. S has 1 orbital, so we only draw 1 box. Now each electron is represented by an arrow, and an arrow can either have a down arrow or an up arrow. And the up and down arrow describes the spin of the electron. And what we find is that when electrons pair up in the same orbital, they pair up with opposite spins. So here there would always be a down with an up. So that's 2 of our electrons. The next is the second energy level. I'm going to actually move down to this lower line here, and so I can show it here. And at 2s only has 1 orbital again, and it has 2 electrons in it. That's my 4. Now I'm going to need a 2p because I have more electrons to place. I placed 4, I need to place all 8. And so this one, my p, actually has 3 boxes. And I draw all 3 boxes whether I'm going to use them all or not. Now as these electrons load into the p, let me show you what it looks like. So we've got here back to the p. When I put my first electron in, that electron is going to occupy one of these orbitals. So let's say it goes into this peach one first, and it goes back and forth between the peach one. The next electron I add in has an option. It can either jump into the peach with this electron and go back and forth with it, or jump into its own orbital. Now because both those electrons are negative, they're going to tend to repel each other, and so it's going to not pair up. It's going to go into an empty orbital before it pairs up. That's just because they repel each other. So they won't actually start pairing up until they have 1 electron in each of those 3 orbitals. So in our diagram here, the way we show that is we come over here to P and we have 4 electrons still to place. So we say, okay, so there's 1, there's 2, there's 3. They've put in separate orbitals. I still have 1 more to go, so now they have to start pairing up. And that's where my 4th electron goes. So here I've got these 2 electrons open. Awesome. That's the orbital diagram for oxygen. Now the shell diagram. So we have what we do is we draw the nucleus, plus 8. So I can't see it now, but it's a plus 8 there for 8 protons. And then I know I'm going to have 2 energy levels. So I'm just going to draw the energy levels. I'm going to put an electron here, electron here. I'm going to do another energy level. Now I'm going to put an electron here, 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 here. 1, 2, 3, 4, 5, and 6. So let's talk about some of the strengths and weaknesses of these 3 models. So over here we have a pretty streamlined version. This one is easy and quick to write. This one is harder to write, but it also emphasizes the orbitals. Whoops. And another thing it does is it shows you how many unpaired electrons there are. And what we're going to find is whenever there's an unpaired electron, that's going to be a place where a bond is likely to happen. So oxygen, it looks like, is likely to form 2 bonds, one with each of these unpaired electrons. So it also shows unpaired electrons, which also gives you some hints as to number of bonding sites. So we would say oxygen has 2 bonding sites. It'll create 2 bonds, either with 2 different things or a double bond with one thing. Now this last diagram is a pretty nasty simplification. It leaves out all the shapes of the S's and the P's and just puts the same ones on the same energy level. And this is really good for emphasizing which energy level. So it's good for emphasizing valence energy levels and valence electrons. So if you're really worried about wanting to show how many electrons are valence and how many are inner electrons, this is a great diagram. It's quick and easy to draw. If you want to show more about the orbitals, here's a great way to express it right here. If you want just a quick and easy way to figure out where the electrons are and in which sublevels, but maybe you don't care so much about the orbitals, you can draw it this way. So it's 3 representations that have their strengths and weaknesses. And we're using all 3 of these in the future. Now, using the periodic table. I don't know if you've ever wondered why the periodic table has this wild shape to it. And the reason it does is because when this periodic table was developed in this shape, we didn't actually know anything about electrons. We just knew about properties of stuff. And people started finding, hey, if we stack the things that have similar properties, so all of these halogens react in a similar way when we react them with stuff, they started grouping them into this vertical group. And when they did that, they saw, oh man, look, a lot of these things just line up really, really well with things they react with similarly. And then we found out that that's because they have similar electron structures. So this periodic table actually tells you the electron structure of the atom. Now notice we said that the first energy level has an S sublevel and 2 electrons possible. Notice how the table is broken into these components. And now these are the energy levels, 1, 2, 3, 4, 5, 6, 7. So first energy level. Notice how there's, this one we want to move hydrogen, or helium, sorry, over here and put the box here instead. So notice how each one of these are 2 wide. That's 2 electrons for the S sublevel. I'm going to put an S here. Any boxes here in the periodic table represent an S sublevel electron. Then on this side, notice how these are 6 wide. So our next, so these guys are 6 wide, so that's our P's. And then this and through here are our D's, and they are, sure enough, they are 10 wide. Whoops, 10 wide, so those are our D's. And down here are our F electrons. So let me erase some of this stuff real quick. So how do we use the periodic table to help us with electron configurations? Here's the simplest way. So for any element on the periodic table, let's do one that's straightforward at first. Let's do sulfur. The first thing I like to do is look at where sulfur is. It's in the 3rd energy level. So it's going to have the outer energy level of its electron cloud. It's going to have 3 energy levels. So the outer energy is the 3rd. And I know that because it's in the 3rd row of the periodic table. That's how cool this is. Now I know that my 1 first energy level is here, 2 here, 3 here, 4 here. My first energy level has 2 electrons because there's 2 squares in it, 2 electrons. So I know this is going to be a 1s2. Second energy level, so I go from 1, 2 down to 3. The next electron I load in is going to be in the second energy level in the s block, and there's going to be 2 of those electrons. So 2s2. So that takes care of that box, that box, that box, that box. Now the next box in the periodic table is here. And I know that's the p's sublevel. So 1, 2, 3, 4, 5, 6. And it's going to be 2p6. It's 2 because second energy level. That takes off all of those. And we just keep this process up until we reach our good friend sulfur wherever we are. So I come down here, third energy level, s electrons, s2. Come over here and we're like, okay, these are the p's. It's 3p, so it's 1, 2, 3, 4. So 3p4. And then I'm done now because I've gotten the sulfur. And sure enough, I have all the electrons I need to have. That is how to use a periodic table. Let's do one that's a little harder. Let's come down here and do, let's not do one that's too terrible. Yeah, let's do one that's really terrible. Let's do one together. Bismuth. Woo! So I know the valence energy level is going to be the 5, 6 energy level. So I'll do a quick erase here of these guys. And let's do it. So my first 2 electrons go into the 1s. So 1s2. My next 2 go into 2s. 2s2. The next 6 go into 2p. So I'm going to say 2p6, and that gets me through all of those. Now this next one goes into 3s. The next goes into 1, 2, 3, 4, 5, 6. 3s2. 3p6. So now I get here and I'm like, okay, so I know the third energy level have an s, a p, and a d. But on my periodic table, the next box is in the s subblock. And sure enough, that is where it falls. So it happens that the 4s has lower energy than the 3d. So at 4s2. So I say 4s2. And then I'm counting across. I have to remember now, oh wait, these are not 4d electrons. The next d that needs to be filled is in the third energy level. All these through here, even though in the fourth energy level, are backfilling to the third. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10. Then I pop over to here and I'm like, okay, so those were 3 p's here. This must be 4 p's. So 1, 2, 3, 4, 5, 6. 4p6. I just keep doing this until I get there. I jump down here and I say, oh, what's next is fifth energy level, s electrons. 2 of them. 5s2. And then I get here and I'm like, all right, those were 3Ds, so this must be 4Ds. The Ds are always back one level what they look like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're looking at 4D10. And then back up to 5, 5P, 1, 2, 3, 4, 5, 6. 5P, 6. We're almost there. Now we're down here on 6S2. And we say, okay, 56, 57, wait a second. And I look down here and I go, oh man, 57, then goes on to 58. So these are F electrons. Now wait, back here at 4D, I should have had a 4F, because that's where my first F shows up. So these must really be 4F electrons, 2 energy levels below where they show up in the periodic table. So the D's backfill 1 level, the F's backfill 2. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. Now this periodic table is organized weird. It should really have 57 down here, and that 71 should be up here. So 57 through 70 in this periodic table, that's the F's. So that's 4F, 14. And then jump up here to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those are the 5D10. I'm going to put it down here. Maybe I shouldn't have done this is a hard one. And then up to here is 1, 2, 3, and that is 6P, 6P3. Woo! That is a pain. Now there is a slightly easier way to go. You can do a simple notation and start with the noble gas directly below on the row above where you want to be. So for bismuth, instead of writing all of this up to right here, I can do it this way. I can put a bracket, xenon, and what that means is this should be the electron configuration of xenon plus 6s2. So I'd be on here 6s2, 4f14, 5d10, 6p3. Wow, so if you got that one, you're squared away and you really know what's going on with this stuff.